In the earlier slides, we have already seen how to derive the term symbols, whereby the state of an atom is the conditions of motions of all the electrons. To specify a state, one must list 4 quantum numbers for each electron, which are the principal quantum number, angular momentum quantum number for the orbiter, and the angular momentum quantum number with reference to the z-axis for the orbiter, as well as the spin quantum number. While in the term symbols, it groups all the state with the same energy into one level. So a level is a collection of state having the same energy in the absence of an external electric and magnetic field. So now we continue with the system with more than one electron. Electrons in an atom occupies orbiter of the same type and shape as the s-p-d-f orbitals of hydrogen. The only difference is the energy. There are 3 building up rules that needs to fulfill in order to arrange the electron in the orbiter. So Pauli exclusion principle states that the value of the principal quantum number, the orbital angular momentum quantum number, the orbital angular momentum quantum number with reference to the z-axis, and the spin quantum number with reference to the z-axis must be different for all the electrons which is occupying the orbiter. So the electrons tend to occupy orbiter with the lowest energy, and according to the Hund's rule, the electrons tends to occupy the degenerate orbiter with the parallel spin before they pair up. When a set of orbitals of a given n and L is fully filled, it is referred to as closed shell. Closed shell makes no contributions to the orbital or the spin angular momentum for the whole atom. Therefore, when we determine the term symbols, we do not consider the electrons which are occupying the closed shell. Elements such as lithium, sodium, potassium, rubidium, and cesium have the similar spectra to hydrogen with the similar J-splitting, because they are all come from the same group. Therefore, they have only one electron in the electron valence. The splitting due to the coupling of L and S will increases remarkably with the atomic number. If we refer to the electron configurations for lithium, sodium, potassium, and so on, we will see that they have the same spectrum to the hydrogen atoms, because all of these elements, they have only one electron in the s orbital. Format of the term symbols for many electrons is same to the one electron system, whereby we have the superscript corresponding to the multiplicity, the state symbol L, which is the total orbital angular momentum quantum number, and the state symbols has the symbol of S corresponding to L equals to 0, state symbol equals to P corresponding to L equals to 1. When L equals to 2, the state symbol is D, and so on. So the energy levels of the Hamiltonian also depends on the L and also the S as well. For many electron system, because you have more than one electron, therefore they will have some complexity which involve how to allocate the electrons in the orbiter or arrange the electron in the orbiter. For non-equivalent electrons where they have the different principal quantum number or the orbital angular momentum quantum number, for example, if you have 2 electrons in the p orbiter, then these 2 electrons will be occupying the 2p orbiter and also the 3p orbiter, or they will be occupying the 2s orbiter or 2p orbiter. So by using this Clebsch-Gordon series, we can couple the individual orbital angular momentum and add the individual quantum number for electron 1 and electron 2. So we can obtain the total orbital angular momentum quantum number, which is L, capital letter, equals to orbital angular momentum quantum number from electron 1 plus the orbital angular momentum quantum number from electron 2. So when we sum up the orbital angular momentum for the electrons, then we will be able to obtain the maximum total orbital angular momentum quantum number. And similarly, when we find the difference between these two orbital angular momentum quantum number for each of the electron, then it will result in the minimum value for the total orbital angular momentum quantum number. So in between this maximum and minimum value, when we minus 1 for the maximum value until we can get the value which is reach this minimum value, which means that if we get 4 here, 4 minus 1, then we will get 3 until we get the minimum value. For example, for a system with 1 electron in 2p orbital and 1 electron in 3p orbital, so these 2 electrons in occupying the 2 different p orbital, while the orbital angular momentum quantum number for electron 1 is equals to 1, and similarly electron 2 also occupying the p orbital, so the orbital angular momentum quantum number L2 is also equals to 1. Therefore, we will be able to find out the total orbital angular momentum quantum number for both of these electrons with the maximum value equals to 1 plus 1 and the minimum value is 1 minus 1. Therefore, the range is between 2 and 0. From 2 and 0, we have to minus the maximum with 1. So we get 1. 1 minus 1, we will come to the minimum value. Therefore, these are the 3 possible values for the capital letter L, which is the total orbital angular momentum quantum number. So the code for converting the value of L into a letter is D state, P state, and S state. Therefore, the capital letter X in the term symbol corresponding to these configurations, it has 3 different values. One is L equals to 0, corresponding to S term, L equals to 1, corresponding to P term, and L equals to 2, corresponding to D term. So the terms are different in the energy on account of the different spatial distributions of the electron and also the difference in the repulsion between the electrons. So if there are 3 electrons in the orbital, then we will need to couple the first 2, followed by using this result to couple with the 3rd electron. And there are 2 examples here, 2 electrons in d orbital as well as 3 electrons in p orbital. If we look into this example A, so we will be able to find out the total electron in this d orbital. It has a L1 equals to 2 and L2 also equals to 2. So the minimum value for the capital letter L is equals to 2 minus 2 equals to 0, while the maximum value equals to 2 plus 2, then you will get 4. In between 4 and 0, we have to fill in the range, which we minus out 4 with 1, we get 3. 3 minus 1, we get 2. 2 minus 1, we get 1. 1 minus 1, we come to the minimum value. Therefore, for these configurations, 2 electrons in d orbital, it will contribute to 5 different terms with the respective G equals to the state of, for L equals to 4, and then when L equals to 3, the state is F. When L equals to 2, the state is represented with the D state. When L equals to 1, represented by the P state, and L equals to 0, represented by the symbol of S. For 3 electrons in the p orbital, we have to couple the first 2 electrons and then use the result to couple with the 3rd electron. So just now we have already seen when we couple 2 electrons in the p orbital. Okay, coupling two electrons give a minimum value of 0 because electron 1 in p orbital, so the L value is 1. Second electron also in p orbital, therefore L2 is also equals to 1. So L minus 1 when 1 minus 1 will get 0. Therefore, the L prime consider only two electrons equals to 1 plus 1, 1 plus 1 minus 1 and 0. So we will get the range for two electrons in the p orbital, which are 2, 1, 0. Because the minimum value is 0, the maximum value is 2. So in between, we will have only one value, which is 1. Then we get 2, 1, 0, which is the L prime, results from the coupling between two electrons. Now we couple with the third electron. So L3 is equals to 1 because the third electron also occupying the p orbital. So we have the results from two electrons, 2, 1, 0, coupled with the third electron. Therefore, we will get L prime plus L3. We get maximum value, which is 3. 2 minus 1, we get 1. So 3 minus 1, we get 2. 2 minus 1, we get 1. Similar to this coupling. 1 plus 1, we get 2. 1 minus 1, we get 0. 2 minus 1 will be 1. 1 minus 1 will comes to 0. And last one, 0 plus 1, we get 1. Okay, 0 minus 1, we get minus 1. We have to ignore minus 1 because the quantum number must be the positive integer. Therefore, in these three electrons in the p orbital, the total orbital angular momentum quantum number L, we have 1 F state come from the L equals to 3 and 2 D state come from L equals to 2 and then 3 P state come from L equals to 3, L equals to 1. Okay, we have 3, 1 here. So they are the P state and last one is S term come from L equals to 0. Spin quantum number for electron is 1 over 2. Therefore, for more than one electron in the system, we also conduct the same determinations of the total spin quantum number for the electron, whereby we find out the summations which will get the maximum value, which is S1 plus S2, and lastly find the minimum value S1 minus S2 with the modulus, so it must be a positive value. After that, we fill in the gap in between the maximum and minimum value. Multiplicity equals to 2s plus 1. So this is the value for the superscript in the term symbol. A single electron will give a doublet term symbol because it has only one electron, so the spin quantum number equals to 1 over 2. So 1 over 2 multiply 2 plus 1, you will get 2. Therefore, it is a doublet. But for two electrons in a closed shell, the electrons are all pair. So one will be spin up and one will be spin down for a closed shell. Therefore, the total spin quantum number will be equals to 0. And there is no net spin for a closed shell. So when S equals to 0, the multiplicity is equals to 1. So the term symbol for the multiplicity is singlet S for a closed shell system with a pair of electrons in the orbital. While for two electrons that are not in a closed shell, then there are more possibles for the spin state. We can find that the maximum value, which is electron 1 spin quantum number half plus electron 2, the spin quantum number is also half, so total is equals to 1. And then half plus half minus 1, we will get 0, or alternatively 1 over 2 minus 1 over 2. The minimum value is also equals to 0. Okay, so the spin quantum number for two electron system is either 1 or 0. For two electron system, each of which has a spin quantum number equals to 1 over 2, only two total spin states are permitted which is 1, s equals to 0 and s equals to 1. For the state with s equals to 1, it has only one value of sz. So sz equals to 0, and it is a singlet because if you substitute s equals to 0 into the multiplicity, you will get the value of 1. While for the state with s equals to 1, we can have three values of the sz, which is plus 1, 0, and minus 1. So similarly, when we substitute the value of s equals to 1 into the multiplicity equations, which is 2s plus 1, then we will get 3 corresponding to the triplet. For a closed shell, the electron occupy all the possible orientations so that the net L and S of the shell is 0. Therefore, when working out term symbols, we need to consider only the electrons of the unfilled shell. For a single electron outside a closed shell, the value of L is same as the value of small letter l, just like one electron in the system. For example, for the configurations of neon 3s1, so there is only one electron at the electron valence. Therefore, it has the term symbol of S term. Here are other examples of the closed shell, such as the helium and also the neon. So helium, beryllium, the configurations of the electron is 1s2, for beryllium is 1s2, 2s2. So when we arrange these two electrons in the orbiter, it will be paired up. The total orbital angular momentum quantum number with reference to the z-axis for these two elements are equals to 0 because both are in the Lz. L value Lz equals to 0. So L also equals to 0. While for the Sz, one spin up, which is plus 1 over 2, one spin down, Sz is minus 1 over 2. So the total Sz is 0. Therefore, the S is also 0. So the term symbols for this closed shell is singlet S. And same to the neon. Neon has 6 electrons in the closed shell. So this is the configurations. So they have 6 electrons which fully fill the p orbital. Therefore, the total Lz is equals to 0. Electron 1 in Lz equals to plus 1. Electron 2 also in Lz equals to plus 1, but in the spin down manner. So we have electron 1 and then electron 2. Electron 3 spin up in orbital Lz0, spin up. Electron 4 in the Lz equals to 0, which is spin down, this one. The fifth electron in Lz equals to minus 1, spin up. And the last one, spin down in Lz equals to minus 1. So the total Lz is equals to 0, plus 1, minus 1, 0, 0, 0, minus 1, plus 1, 0. So the total Lz is 0. Therefore, the L value also equals to 0. While for the Sz, spin up, spin down is equals to 0, plus half, minus half, 0, plus half, minus half, plus half, minus half. So the total Sz is equals to 0. Therefore, the S is also 0. And the term symbols for the neon is also equals to singlet S, where L equals to 0, the state symbol is S, and the multiplicity is equals to 1 because S equals to 0, so 2S plus 1 equals to 1. Therefore, for a closed shell system, the term symbol is singlet S. Now we move to the coupling effect, where the coupling can be understood as a perturbation process, and many electron Hamiltonian operator can be written as this state of expressions. So this first term is the unperturbed hydrogen-like Hamiltonian associated with the orbital, SPDF, while the second term here is associated with the electrostatic interactions, and the third term here is associated with the magnetic spin coupling. The three terms represent the level of the interactions or the coupling between the electrons. Next is on the total angular momentum quantum number. Quantum number J tells us the relative orientations of the spin and orbital angular momentum of a single electron. The total angular momentum quantum number, capital letter J, for more than one electron system does the same for atom with several electrons. Single electrons outside a closed shell that we have seen just now, whereby the J spin-orbit coupling is due to the one electron. Therefore, we substitute here with 1 over 2. So the value is L plus 1 over 2 or L minus 1 over 2. While for many electron systems, the spin-orbit coupling can be determined using two different ways. Number one is Russell-Saunders coupling, where the spin-orbit coupling is weak and applied for atoms of low atomic number. So they determine the total Li, where from here they find out what is the value of the respective orbital angular momentum quantum number. And similarly, they find out the total Si, or the total spin quantum number with reference to the z-axis. And then from here they find out what is the value of the spin quantum number and subsequently determine the value of J equals to L plus S. Example, the permitted value of the total angular momentum quantum number J. It can be determined using the L plus S to find out the maximum value and also the modulus L minus S to find out the minimum value. After that, fill in the gap between the maximum and minimum value. Example, if you are given a triplet D term of the configurations of neon 2p1 and 3p1, and it is given that the total Lz is equals to L and the total Sz is equals to S, where L is equals to 2 and S equals to 1. So the permitted value for the total electronic angular momentum quantum number, they are L plus 1, which is 3, and L minus 1, which is 1. So 3 and 1, in between you have 3 minus 1, you will get 2. So 2 is one of the value for total electronic angular momentum quantum number, and 2 minus 1 you will comes to the minimum. Therefore, the term has three levels, which are triplet D3, triplet D2, and triplet D1. We can determine the number of levels through the term symbols. When the L is greater than S, the multiplicity is equals to the number of levels. For example, doublet P, the value of L is 1, whereby the value of S is 1 over 2. So in this example, the L is greater than S. Therefore, the multiplicity, which is 2, will represent the number of levels. So doublet P term has two levels, which are doublet P 3/2 and doublet P half. For triplet D term, it has three levels, where in this example here, the L is equals to 2, the spin quantum number S is equals to 1. So again, L is greater than 1, therefore the multiplicity is equals to the number of levels. So it has three levels here, triplet D3, triplet D2, and triplet D1. However, that is not the case when L is smaller than S. If L is smaller than S, then there are only two L plus 1 different J values, which is less than the multiplicity. For example, doublet S term has only one level, which is doublet S 1 over 2. So this is only applicable for L plus S to determine the number of levels. Example, the configurations of neon 3s1, one electron in s orbital, so the configurations has J equals to 1 over 2, and because one electron is in the s orbital, so the L is equals to 0, while the spin quantum number for one electron is 1 over 2. So the term is doublet S. It has a single level only, which we denote it as doublet as 1 over 2. And for one electron in p orbital, the configurations has L equals to 1 because of p orbital where the electron occupied. Therefore, the value of J is 3 over 2 and 1 over 2, where this is come from L plus S. So 1 plus 1 over 2, the spin quantum number S is equals to 1 over 2. So 1 plus 1 over 2, you will get 3 over 2. 1 minus 1 over 2, you will get 1 over 2. Therefore, you have 2 J value. And the doublet P term therefore has 2 levels, doublet P 3 over 2 and doublet P 1 over 2. And these levels lie at different energy on account of the effect of this magnetic spin-orbit interaction. This method to determine the JJ coupling or the spin-orbit coupling effect is through this JJ coupling, where Russell-Saunders coupling fails when the spin-orbit coupling is large, where if you have a large or heavy atoms and high Z value, so individual spin and orbital momentum of the electrons are coupled into individual J values, then these momentum are combined into a grand total, meaning that they consider the individual electron what is the respective Lz value and also the Sz value. So from there they find out the respective Jz value. After that they sum up all the Jz value to deduce the J value, the total electronic angular momentum quantum number for the system. And we use the method 1, which is more suitable for small to medium-sized atom, and this JJ coupling method is better applied for large atom. So we shall only consider the method number 1. By having the value of J, L, and S, then we can label each term that arises from the coupling. So the labeling of the state or the term symbols follow the scheme of 2s plus 1. L is the state symbol, subscript J is the spin-orbit coupling effect. After derive the term symbols for one configurations, then we need to arrange these term symbols accordingly with their respective energy. So the most stable term symbol is the term symbols with the lowest energy, and the arrangement of the electron is to spread out the electron before pair up. And the state of the lowest energy for given electronic configurations is that having the greatest multiplicity. So meaning that the term symbols that has the highest multiplicity will be the one that is the lowest in the energy. If more than one state has the same multiplicity, then the lowest energy of this is that with the greatest L value. If you have the term symbols with the same multiplicity, then we have to refer to the value of L. If the value which is the lowest, then it has the highest value of the energy. So the greater the value of L, the lower is the energy. If the state have the same value of L and S, then for a subshell that is less than half filled, state with the smallest J is the most stable. On the other hand, if the subshell is more than half filled, then the state with the largest value of J is the most stable. Okay. For example, one electron in p orbital, we have derived two term symbols. And these term symbols here, we have the same multiplicity, doublet, and also the same state symbols. Therefore, we need to refer to the J value. So between these two, the J value, which is 1 over 2, is the lowest in the energy compared to the 3 over 2, because you have only one electron in p orbital. The orbital is not half filled. Please try to answer these questions and submit your solutions in Spectrum. Thank you.